let's discuss the graphs for motion. So first of all, we'll discuss the position versus time graph, how the position versus time graph for various kinds of motion looks like, then the velocity versus time graph, and then the acceleration versus time graph. Okay, so now let's suppose your object is at rest. What will be its position versus time graph? How will it look like? This is x versus t. Tell me. Suppose it is at position x0. So what will be its graph?
Sir, a line parallel to x-axis.
It will be line parallel to x-axis or time axis?
Time axis.
Time axis, right? So your particle is at this position, suppose at t equals to 0. As time passes, the particle is still at the same position, right? At this time also the particle is at same position. Then at some other time, at this time also the particle is at same position. So it's going to be a straight line parallel to the time axis. Okay, like this, if you join all these points. Then now this is for object at rest. Now let's suppose your object is moving, okay, and object is performing a uniform motion. Object is performing a uniform motion, that is motion with constant velocity. And suppose your object is starting from this position, we can call it x0. Particle is starting from x0. So now this is for uniform motion. How will this graph look like? If velocity is constant, so it will cover equal distances in equal intervals of time. Okay, so see what will happen. Okay, let me change the x0. Okay, so let me take it at origin. So this is suppose x0. So I can say in 1 meter it covers distance, in 1 second it covers distance equal to 1 meter. Okay, so in 1 second, this is 1 second, t equals to 1 second, it goes here. Okay, so this will be your point, right? This will be your point. Okay, it starts at this position at t equals to 0, it goes till here at t equals to 1, then at t equals to 2, again it will cover the same distance, right? It will cover the same distance. So for t equals to 2, your object will be here. Okay, for t equals to 3, again it will cover same distance because it is moving with uniform velocity. Okay, so you will get these points. Okay, and if you join all of them, you will get a straight line. Okay, you will get a straight line like this. Okay, and now see, you can say this is x0, you can take some x1, suppose this is x2. Okay, this is at time t1 and this is at time t2. And if you take slope of this straight line, it will be x2 minus x1 divided by t2 minus t1. So using that you can find out the velocity. Okay, v is equal to x2 minus x1 divided by t2 minus t1. We discussed this in last class also. So right, this is clear. For uniform motion you will get a graph like this. Yes, no?
Yes, sir. Yes, sir.
Okay, now what if the velocity is increasing? What will happen? The graph will be curved, right? So if velocity is increasing, it will cover more distances in same time, you can say. So the graph will be like this. Okay, what if the velocity is decreasing? Then the graph will be like this. Okay, this is for velocity decreasing. Okay, so I can draw uniformly accelerated or uniformly retarded motion. So for them, okay, so this is x, this is t. For uniformly accelerated motion, the graph will be like this. Okay, velocity is increasing. For uniformly retarded kind of motion, retarded meaning with negative acceleration, okay, the graph will be like this. Okay, so this is for uniformly accelerated motion. This is for uniformly accelerated motion. And this one is for uniformly decelerated motion, you can say, or uniformly accelerated motion with negative acceleration, or uniformly retarded motion. Okay, is it clear?
Yes, sir. Yes, sir.
Right. So these are position versus time graphs. And what do you get from the position versus time graphs? You get the velocity. Okay, you get the velocity. Next, let us talk about the velocity versus time graph. Okay, so these are xt graphs. These are xt graphs. Next, let's talk about the vt graphs. Velocity versus time graphs. So, how will the velocity versus time graph look like if object is at rest? Tell me. How much velocity does it have? Zero velocity, right? Okay, object at rest, velocity is 0. So at t equals to 0, velocity is 0. At t equals to 1, velocity is 0. At t equals to 2, velocity is 0. Right, this is v, this is t. At t equals to whatever time, the velocity will be 0. Okay, so how will your graph look like? It is just the time axis. Okay, it is just the time axis. This is clear?
Yes, sir.
Okay. Next one, object is moving with uniform velocity. Object is moving with the uniform velocity. So tell me. This object is also moving with uniform velocity, just that the velocity is equal to 0. Right? This velocity is equal to 0. So now instead of 0, suppose you have some velocity, 1 meter per second, 2 meter per second, anything. Okay? So suppose velocity is equal to v naught. Right? V naught can be anything. Let's suppose it is 2 meters per second for an example. Okay, this is 1, this is 2, so 2 meters per second. So at t equals to 0, it is 2 meters per second. At t equals to 1, it will be 2 meters per second. At t equals to 3, it will be 2 meters per second. Right? So you will get a graph like this. So at t equals to 0, it is v naught. At t equals to 1, it's same. At t equals to 2, it is same. At t equals to 3, at t equals to 3, it is same. Right? So this is 1, 2, 3, and the velocity is v naught, v naught, v naught. So if you join these points, you will get a graph which looks like this. Okay? A straight line parallel to time axis. This is for uniform motion. Oh. This is for uniform motion with some constant velocity. Now, how will the velocity versus time graph look like for uniformly accelerated motion? So can you tell me? Uniformly accelerated motion.
Straight line, sir.
Straight line. What kind of a straight line? With positive slope, negative slope.
Positive slope, sir.
Positive slope, right? So uniformly accelerated motion will be like this. Okay, it will have some initial velocity at t equals to 0. At some time t, its velocity will increase, right? So this is uniformly accelerated motion. And for uniformly retarded motion, its initial velocity will be more. As time increases, its velocity will decrease, right? So this is uniformly accelerated motion. This is also uniformly accelerated motion, you can say, but with negative acceleration. Okay. So this is velocity versus time graph. So this is for uniformly accelerated motion, and this is for uniformly retarded motion. And now see, you know, now this is uniform acceleration. Now how will the graph look like if the acceleration is increasing? Simple, this is uniform acceleration. How will the graph look like when acceleration is increasing or decreasing?
Curve, sir.
It will be a curve, right? It will be a curve. So if acceleration is increasing, the graph will go like this. If acceleration is decreasing, the graph will go like this. Okay, so I will show it using a dotted line. Not this one. So this is increasing acceleration. This is for decreasing acceleration. Okay, so all right, I will just copy paste it on the next page because there will be too much information. Okay, so this is decreasing acceleration. Right, and this one is with increasing acceleration, and this is for uniform acceleration. Okay, right? So this is clear for everybody. Okay.
Yes, sir.
So now you tell me what are the things that you can find out from the velocity versus time graph?
Displacement, sir.
You can find out displacement, and what else? Acceleration, right? So you can find out displacement, you can find out acceleration. So how can you find out displacement?
D into T, sir.
It is
Velocity into time.
right. And okay, from the graph, what will that thing look like on the graph?
Slope of velocity and time graph.
Slope will give you displacement or acceleration?
Sir, area gives the displacement, whereas slope gives the acceleration.
Right, good. So area will give you displacement, slope will give acceleration. Okay, so just in case it is being very fast. Okay, it's not being fast, right? Okay, so suppose you have a graph like this. Okay, this one is good for explanation. So suppose this is some, okay, let me change this. So this is time t1, this is time t2, okay, and this is uniform motion. So v is constant, right? So now you know how can you find out v. So v is equal to what? x2 minus x1 divided by t2 minus t1, right? So now if you move this t2 minus t1 on the other side, what do you get? You get x2 minus x1. So x2 minus x1 is just v multiplied by t2 minus t1, okay? And what is this thing on this graph? So you can see length of this side is what? It is v. If you consider this side, okay, this much distance, okay, this much length is, you can say this much length minus this much length. So this is t2 minus t1, okay? So this length is t2 minus t1 and this length is v. So if you multiply this length with this length, what do you get? You get the area, right? You get the area. So this area, okay, it's not looking good. So this area will give you what? It gives you x2 minus x1, and that is displacement, right? So this was an example, but we can conclude something. So what can we conclude? We can say that the area under velocity versus time graph gives us displacement, okay? So area under the, I can just say displacement is equal to area under VT curve or VT graph, right? Okay, all right, this is clear.
Yes, sir.
Everybody?
Yes, sir.
Okay, then you take this VT graph, the uniform acceleration. Okay, this is just for explanation. So now see, you have some initial velocity. So this is u at time t1, okay, let's call this time t1. Okay, and you have some velocity at time t2, okay, this is time t2, and your velocity is at this time is this much, okay? Initial velocity generally we denote by u, or v naught. Final velocity will denote by v only. So I can find out acceleration. So acceleration is equal to what? A is equal to v2 minus v1, or I can say v minus u, okay, divided by t2 minus t1. And what is that thing? So if you take v2 minus v1, okay, let's say v2 minus v1, so v2 is this much, okay, v1 is this much. So if you take v2 minus v1, it is this much distance, okay, we call this rise. Change over the vertical axis, we call this rise, okay, and change over the horizontal axis, we call this as a run, okay. So this is called as, rise, and this one is known as run. Okay, right? So rise or run, or change over the vertical axis divided by change over the horizontal axis, gives you what? It gives you slope. It gives you slope of the curve. Okay, in this case the curve is line only, so this will give me what? Slope of this line, right? And if this angle is theta, then the slope is equal to tan of theta, right? The opposite side divided by the adjacent side. Okay, so slope of the velocity versus time graph gives you acceleration. So here I will just say it is tan of theta, and the slope of VT graph gives acceleration. Okay, so out of, see, xt graph, vt graph, and you will have another graph, that is the acceleration versus time graph. So out of these three, which one is most useful? If you want to study the motion, which one would be most useful? Which will give you, yeah, VT gives you most information about the motion, the information that we need. Okay, we need to know the displacement, we need to know the velocity, we need to know the acceleration. If we know these things, that means we know about the motion. So it is the graph of velocity versus time. Okay, so by looking at the graph only, you can say what is the velocity at a particular time. Then if you find area under the curve, you will get displacement. Okay, so you will not get particular position, right, but you will get displacement. And then if you find out slope of the graph, you will get acceleration. Okay, so velocity versus time graph, it is fully packed with information, right? There is lot of information in the velocity versus time graph. So is this thing clear?
Yes, sir. Yes, sir.
Okay, and the next one or last one that we are interested in is acceleration versus time graph. So now the acceleration versus time graph for uniform acceleration, or first for uniform velocity, how will it look like? For uniform motion, this is A versus T. And okay, tell me, how will it look like if motion is uniform? It will be a, it will be a line, right? So if motion is uniform, how much is acceleration?
0, sir.
Acceleration is 0, right? So graph will look like this. Okay, just parallel to time axis, because at any time the acceleration is 0 only, 0 0 0 0 0 at any time. Okay, so this is for uniform motion. Now for uniformly accelerated motion, how will the graph look like?
Straight line with positive slope.
Straight line?
Pass through origin, sir.
No. Okay, passing through origin, but this one is also passing through origin.
Positive slope, sir.
For uniformly accelerated motion, okay, acceleration is uniform. So what does it mean when I say acceleration is uniform? Uniform means constant. Okay, so now can you tell me
parallel to the axis, sir.
Parallel to t-axis, right? It's a straight line parallel to t-axis. So this is A at start. I can say it is A naught at t equals to 0, and at any time the acceleration will be same. Okay, so at this time you have same value of acceleration, at this time you have same value of acceleration. Okay, you have same value of acceleration, so the graph will look like this. Okay, and now if I draw graphs like these, I'm sorry, if I draw graphs like this is acceleration versus time graph, this is also acceleration versus time graph. So what does it mean? This is AT graph, this one is also AT graph. So this is this uniformly accelerated motion?
No, sir.
No, this is not uniformly
No.
accelerated motion. So in this one your acceleration is increasing, in this one acceleration is decreasing, right? So not uniformly accelerated motion. So this is for increasing acceleration, and this is when acceleration is decreasing. So decreasing acceleration. Okay, so there is one more information, your acceleration is increasing. So now acceleration is increasing with the constant rate. Okay, acceleration is increasing with the constant rate, right? Okay, so these are the kind of graphs that you can see, okay, in most of the cases. And then what information will you get from AT curve, AT graph?
Change in velocity, sir.
You will get change in velocity. Okay, so I can pick this one or anyone actually. Okay, you can take this one, anyone. Okay, the area under AT graph will give you change in velocity. What happened? Okay, so let's suppose this is acceleration at t1, this is acceleration at some time t2. Okay, this is t1, this is t2, right? So we know acceleration is v2 minus v1 divided by t2 minus t1, and therefore v2 minus v1 is equal to what? A times t2 minus t1. Okay, that is area under the curve. Right, so area under the velocity versus time graph gives you the change in velocity. Area under acceleration versus time graph gives you change in velocity. Okay, so are the things clear? Is there any doubt in this?
No, sir.
No, sir.
Okay, so I am taking these things slowly and in detail because there can be questions based upon this, and okay, that is first thing. And second thing is, this is useful for the entire course. Okay, so now next we'll learn about the derivatives and integrations. So do you know about derivatives and integrals? If you know, we can keep it short.
Yes, sir.
Okay, everybody?
Yes, sir.
Yes, sir.
Okay, so then we can keep it short, otherwise okay, we can take extensive lecture. Okay. All right. So now this is a position versus time graph, and I want to find out velocity. Okay, I want to find out velocity. So let's suppose this is my time t1. Okay. So this is my time t1, and I take some time. Oh. All right. So now, okay. Now this is my position versus time graph, and I want to find out velocity of this object, okay, of the particle whose graph this is. So I take some time t1, I take some time t2, and this is my position versus time graph. So I mark 2 points corresponding to this time and this time. So this is time t1, this is time t2. Okay, this is at time t2, right? So this is position at time t1, this one is position at time t2. So if I join these 2 points, I will get a line like this, right? And the slope of that line will give me velocity. Okay? Yes, no?
Yes, sir.
Okay, you get these 2 points. This is x2 at time t2, and this one is x1, position is x1 at time t1. This is first point, x1 at t1, right? So if you join the points, you get this line. Now what will be slope of this line? So change over the vertical axis, x2 minus x1 divided by change over the horizontal axis, that's t2 minus t1. x2 minus x1 divided by t2 minus t1, that means you will get the velocity. So velocity of this object whose motion is like this, okay, whose position is changing like this, okay, you will get from this graph, but it will be average velocity between t1 and t2. Okay, so now what I am doing is I am bringing that t2 closer, okay, closer to t1. So then I get this point. Okay, so let's suppose this is t2 dash. So I will get this point, which I will, okay, which I can denote as x2 dash t2 dash. So this point is x2 dash t2 dash, this point, right? Okay, so I'm writing the vertical coordinate first and then the horizontal coordinate, doesn't matter, right? Okay, so I'm just saying that its position is x2 dash at time t2 dash, right? So I get this another line, I get another line. If I connect these 2 points, the line will be like this. Okay, so if I take slope of this line, what will be the slope? It will be velocity of this object from t1 to t2 dash, right? It will be the velocity from t1 to t2 dash. Okay, yes or no?
Yes, sir.
Yes, sir.
Okay, all right, then I move this time even closer, then what will happen? So if I take t2 double dash, this one, and join, okay, I get this point. So I want velocity between these 2 points, so I join these 2 times, so I will get a line like this. Oh, I will get a line like this. Okay, so can you distinguish between lines, or shall I change the colors? That one was better. This line, oh, blue, I get a line like this. Okay, so now see, can you distinguish between these lines? Yes, no?
Yes, sir.
Yes, sir.
Okay, so what is happening
Yes, sir.
as I am taking the time closer and closer to the initial time? What is happening to these lines whose slope will give you velocity? What is happening to these lines? Can you say that this is your curve and this was your first line? So when you take two distinct times, okay, very distant times, okay, then this line whose slope gives you velocity and this curve, they are very far. Yes or no?
Yes, sir.
Okay,
Yes, sir.
as I move this time closer, okay, as I move, see, as I go from T2 to T2 dash, what happens now? So this line whose slope gives me velocity, compared to this line, this one is closer to the graph,
Yes, sir.
right? And then as I move the time even closer, okay, if I choose even shorter interval, then what happens? This line approaches even closer. Okay, so that means now if I take points very close, then what will happen? Okay, so let me just, so if points are very close, T1 and T2 are very close, so close that you cannot distinguish between the points, you will have to zoom it, okay, 1 lakh times to distinguish between these 2 points. Then what will happen? Then your line whose slope gives you the velocity, it will be very close to the graph. And what does that very close to mean? It means that it will be tangential to the graph. Okay, so it will be tangential to the graph. So see, this is your this is your xt graph. Okay, this is your xt, oh, straight line, right? So this is your xt graph, and I choose these points. I take this point, this is suppose T2 and this is suppose T1. Okay, so this is my T1, this is my T1, this is my T2. So now I join lines, I draw perpendicular lines from T1 and T2. They meet at these 2 points on the graph. So if I draw perpendicular lines from there on the x-axis, I will get x2 and x1. Okay, so now I will get x2 and x1. So see, let's draw the perpendicular lines. So this will be x2, this is x1. And if you join these 2 points, which are very close to each other actually, you get a line. Okay, of course you get a line. So you will get a line like this. Okay, so now if you zoom this, still there will be some difference, okay, between the graph and this line. Okay, there might be some difference, okay, some distance. But now if you take T1 and T2 very close, if you take them very close, then the line that you get whose slope gives you velocity will be tangential to the graph. This is clear?
Yes, sir.
Okay, so now when T1 and T2 are so close, very close, then we find the velocity. We call it as a instantaneous velocity. Okay, we call it as instantaneous velocity. Till now, whatever velocities we discussed, they were average velocities. Okay, they were average velocities. So how can I define the instantaneous velocity? Instantaneous velocity. Instantaneous meaning in an instant. Okay, within split of a second. Okay, instantaneous velocity. So it is velocity at a particular instant of time. V is equal to, you can say, x2 minus x1 divided by t2 minus t1. This is your formula, right? So this t2 minus t1, we write it as delta t. x2 minus x1, we write it as delta x. So delta x and delta t means change in x and change in time, right? So this is our formula of average velocity. Okay, so I will call the numerator as delta x, the denominator as delta t, and now I want to find out this velocity at a particular instant. Okay, so no time is spent in finding this velocity. So t1 and t2 are very close. Then we write it as limit delta t tends to 0. Okay, limit delta t tends to 0. That means the time that you take is very small, so small that it is almost 0. So then we call this velocity as an instantaneous velocity. Okay, and this is precisely the definition of derivative also. So when you write it like this, then it is derivative of x with respect to time. Okay, this is derivative of x with respect to t, right? So change in x taken in time, change in t, okay, delta t. When this change in time, when change in the denominator is very small, almost 0, then it is known as derivative of this numerator, the quantity in numerator, whose change you are taking in numerator with respect to the quantity in denominator. So is the meaning of derivative clear?
Yes, sir.
Yes, sir.
Everybody?
Yes, sir.
Okay, so what does this mean on this graph? What does derivative mean on the graph?
Slope, sir.
Slope of what?
T graph.
Slope
of xt graph.
Okay, see, when I find the velocity from t1 to t2, then is it slope of this graph or is it slope of this line? It's slope of this line, right? because your graph has different slopes at different points. Okay, your graph is like this. Can you say that, okay, this slope and this slope, so can you say if you have two slopes like this, so this slope and this slope, are they equal? Slope means inclination, they are not equal, right? So this line has different slopes at different points in between T1 and T2. So the slope that you are finding is actually slope of this line. Okay, so that means that here you are finding slope, okay, but it is slope of the tangent line to the graph, and it will be equal to, you can say, slope of the graph at this point, because okay, tangent line by definition it intersects the graph at one and only point, so it is slope of the graph also, but it is slope of the graph at this time. Okay, is it clear?
Okay, sir.
Okay or clear?
Yes, sir.
Clear, sir.
Okay, good. So this is, okay, the velocity is derivative of x with respect to t. And what is definition of derivative? So derivative means, on the graph, derivative means slope of a tangent line, slope of a tangent line to the graph. Okay, so if I am taking derivative at this point, means it is slope of tangent line drawn at this point. Okay, so this is meaning of derivative. Okay, and then there are some formulae for derivative which we need to remember. So most common formulae are, actually there is a sheet, okay, formula sheet that I can forward to you. Okay, so yeah, you need to remember those formulae. I hope you you already know the derivatives of some common functions, right? What is x raised to, derivative of x raised to n?
Nx, n minus n.
Okay, derivative of sin x?
Cos x, sir.
Cos x. Everybody knows this?
Yes, sir.
Yes, yes, sir.
Okay, derivative of tan x? Sec square x. Okay, secant square x. Then derivative of cot x? Okay, so if you know, it's good. If you don't know, you have to by heart it. Okay, so I will forward the formula sheet. At least that many derivatives, not at least, those derivatives would be sufficient. Okay, so I will forward you the formula sheet for derivatives and integrals. So now this is derivative. Okay, meaning of derivative. Now if you want to find out the instantaneous velocity, it is slope of a tangent line to the xt graph. Okay, similarly, if you go to vt graph, what will slope of tangent line give you?
Acceleration, sir.
It will give you acceleration, but what acceleration? It will give you instantaneous acceleration, right? So I want to find out instantaneous acceleration at this time. What will I do? I will draw, okay, I will take this time, draw a perpendicular from this time. Okay, so I will draw perpendicular to time axis. It meets this graph at this point. I will draw tangent at this graph, okay, tangent to the graph at this point, right? And slope of this tangent will give me instantaneous acceleration at this time. Okay, so whatever acceleration we studied till now, they were also the average accelerations. Okay, so a is equal to v2 minus v1 divided by t2 minus t1, that is change in velocity delta v divided by change in time delta t. This is average acceleration. I want to find out instantaneous acceleration. It will be what? The derivative of velocity with respect to time. On the graph, it is slope of a tangent line drawn to the velocity versus time graph. Okay, it is slope of a tangent line drawn to the velocity versus time graph. This is clear?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
good. So now next thing is integral. Okay, what is integration? So integration means area under a curve. Integration means what? Area under a curve. Okay, so shall I, yeah, I have a graph, I can explain it here. So see, integration is antiderivative actually. Okay, integration is antiderivative. Do I have that thing? Yes, I have. Okay, so see here, you have, suppose this time t1. Okay, first thing, let us start from here. We know what is area under the velocity versus time graph. It gives me what? It gives me displacement. Displacement change, right? We know this. Area under the velocity versus time graph gives position. Okay, that is displacement. Now it's very simple to find out area if you have a graph like this. Okay, this is just a rectangle. Its area is into length into breadth. Okay, if you have a graph like this, still it is simple. Okay, it will be a trapezoid, right? Its area you can find out. Okay, so any regular shape you have, its area you can find out very easily. But then if you have a curve like this, if velocity changes like this, then what will you do? So here what we can do is to find out area. So the mechanical thing that we can do is to break down this area into several small pieces. Okay, n number of small pieces. I can cut this total area from here to here. Suppose I want to find out the displacement from t1 to t2. So I know displacement is area under velocity versus time curve. So what I will do is I will cut down this total area into n number of small pieces. Then now what I can do, I can take velocity here and I can multiply it with delta t. So delta t is time difference from here to here. So it will give me the area of this rectangle. Okay, then I will move to the next piece. I will take velocity at this time. Okay, and I will move that with this time interval. So I will get area of next rectangle. Again I do the same thing. I move on to the next piece. Again the velocity at this time, okay, is this much. It's this much, right? So I take the area of this rectangle. It will also give me the area of this piece. Okay, this rectangle. So if I add up all these areas, what will I get? I will get area under velocity versus time curve, right? Yes or no?
Yes, sir.
Yes, sir.
Okay, there will be some error. You can see there will be this much error. So see, when I am measuring area of this rectangle, it's not really the area under this curve because I have missed this much area. Okay, I have missed this much area I have missed, right? Okay, so now there will be some error, but approximately I can say that if I add up areas of all those rectangles, what do I get? I get the area under the velocity versus time curve with some error. Okay, so now we know approximately how can we find out area under velocity versus time curve. Okay, so then now this error can be minimized. How can we minimize this error? If we take large number of pieces, if we take infinite number of pieces, okay, then what will happen? This error will be minimized. How you can say? So for an example, if you take, okay, if you take the time interval equal to this, you will get area of this curve, right? Area of this rectangle. Now if you break down the time interval in two parts, what will you get? You will get area of one rectangle which will look like this, okay, which looks like this, and okay, so I'm breaking this interval into two parts, right? So what will happen now? So I will get area of this rectangle. This is first rectangle. Just a second. I will get area of this rectangle plus I will get area of this rectangle. So now you can see what's happening to the error. I have just divided this interval into two smaller intervals. So error is minimized, right? So this was your error. So earlier, so error was this much. This was total error. So now see how minimized is the error. Okay, error will be this much only. Okay, we managed to get this much area, this much extra area, as we broke this total interval, this interval into two small intervals. Okay, so now you can imagine if we break it into more number of intervals, what will happen to the error? Error will become 0. If number of intervals is infinite, error will become 0. Okay, is it clear? Yes or no?
Yes, sir.
Everybody?
Yes, sir.
Okay, or is there a doubt? Sai?
No, sir. Clear, sir.
Okay, good. So then how can I write this down? So if I take area under one such rectangle, I can write it like delta x. It will give me approximately, you can say, displacement from this time to this time. Okay, and it can be written as v at the starting point, this point, multiplied by this time interval delta t. Okay, so delta x is equal to v times delta t. Now if I sum up, okay, this is summation sign. If I sum up all such small displacements, I will get the total displacement. Okay, so I take I break this down into n number of pieces. Then I can write vi is the velocity at start of ith piece. Ith piece means I can go from 1 to n. So when I is equal to 1, this is velocity at the start of first piece. Okay, when I is equal to 2, it is velocity at the start of second piece. So now you can guess this thing will give you what? v1 times delta t will give you the area under first rectangle. v2 times delta t will give you area under second rectangle. So as you go from 1 to n, you will get area under the velocity versus time graph with some error. But now if you take this n to infinity, that means you are breaking down the total area into what? Infinite number of pieces. Okay, so as n tends to infinity, what happens? The error is vanished. So you get the complete area under the velocity versus time curve. And this procedure of finding out an area, it is known as an integral. Okay, so now this summation will change to an integration. So actually we are doing a summation, but the n is infinite, n tends to infinity. Okay, then if number of intervals becomes infinite, then summation becomes integration. Okay, is this thing clear?
Yes, sir.
Everybody?
Yes, sir.
Okay, so now as n tends to infinity, summation becomes integration. Okay, and we write it like this. So if you see this symbol, what is this? Okay, its name is summa. Okay, the name of this symbol is summa, and this is nothing but an elongated s. Okay, it tells you that what you are doing is you are just taking a sum. Okay, s, right, this is integral sign. It looks like elongated s, and it reminds you that you are doing nothing else but you are taking a sum, but now you are taking a continuous sum. Okay, now you are taking a continuous sum, you are not missing anything in between. Okay, so integration is a continuous sum, right? So it is written like this then. So you are taking integration from t1 to t2, that is you are taking a continuous sum from t1 to t2 of v dt. So this delta t is written as dt.